Good morning, everyone. It's an initiative by JSS ATE Noida under the guidance of HOD of EC Department, Dr. Arun Kumar. So, in the last class, we studied about how the Smith chart is built and what are the representation. Today, we are going to study to up to marking a point on the Smith chart and analyzing in detail like what is the region where the resistance is lying, region where the reactance is lying, and the region where the impedance, the intersection of those will be marked. And later we'll know what is the relationship between a reflection coefficient and impedance, admittance and impedance, and what are the features of admittance, why we are going to into the position where we must understand like what is the importance of the impedance also can be considered while learning the process of Smith chart. So let us begin with the class saying that how the simple form of a Smith chart can be written. I have shared you the handwritten notes and I'll be using the same to describe the following. Okay, so let us start with a simple graph representation. Okay, so this is the graph we are going to use. We already know the circle which I have used here, unit circle, constant resistance circle, and the circle which is formed due to reactance is also drawn here, and the region which is inside the unit circle is only considered. That's why I am considering only the these lines in the form, right? These lines of the reactance and negative reactance. We have discussed this. Can go through that lecture again. And resistance circle. This is a unit resistance circle. Okay. So this is how we are basic simple Smith chart looks like. So what we have done is that we had a two coordinate system. One was the polar and Cartesian we discussed in the last video also, like z plane and a gamma plane. So the superposed both of the circles or the plane to arrive at a special coordinate system. So I can say that I have superposed both z plane and gamma plane, so we have created a new coordinate system for plotting an impedance point. This coordinate system what we have drawn here is called as a Smith chart. It's a powerful tool. Let me explain in future. So if I draw a unit circle here, the point here we already discussed in several cases. Find what is the point, what is the value here, what is the value here are already discussed. Just for remembering purpose I have just written this point represent x is equal to infinity, r equal to infinity, and we have written a sentence saying that um, the as the r increases the radius of the circle becomes 0. Okay, so these things are few properties we came across while studying our constant resistance circle, constant reactance circles. These we are studying when we understood these kind of properties. So, first we already know that, but we will understand what are the properties here in terms of sentence or in the form of words. First of all, the constant resistance circle center lie on the positive real axis. Okay, the, all the constant resistance circles lie on the positive real axis. So this is the upper circle where we can find all the constant resistance circle center lie on these positive axes. What are here, 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 like that? You have all the centers lie on the positive real axis. Okay, this is real axis. So all the points lie in the positive half cycle. As the value of r increases, just now we told that as the value of r increases, the center shift towards the RHS. See? So it becomes, the radius becomes 0. We know that, we have seen here that as the r value increases, the r value, the radius will move towards the RHS, right hand side of the RHS. Okay, so next property will be, as the value of x increases, the radius of the circle decreases. Just now I can see here that as the x value increases to infinity, the radius of the circle decreases, and the radius will ultimately goes to 0. The superposition of two circles are seen in the following diagram. Yes, you can see very clearly that the one circle superposition of constant resistance circle is also here, and superposition of constant resistance circle, and this one is constant reactance circles. You can see. So these are few basic properties are followed while drawing a Smith chart. So next we'll go on to the next sheet, next page. Okay, so here we come, superposition of two circles, that is constant resistance circle and constant impedance circle, on the complex gamma plane is called as a Smith chart. So Smith chart definition, you can easily define here, saying that when the two circles are superposed, we will get a chart or a special coordinate system called as a Smith chart. Smith chart is a very powerful tool for analyzing transmission line calculation or problems. Smith charts are readily available for calculation. As we know that it is available, we can get a printout of it and you can work on the lab procedures, or you can work on the transmission line problems anyways. So what and all are the things which are present in a Smith chart? So let us see a blank Smith chart on we'll use that, and we will see what are the important points you can say, or we can use this. Okay, so now we have to see that how it is placed. uh, the right hand side will contains more cluster. If it is more cluster, then we can use that diagram for our That is how we can use it. Hmm? We can use it. That is how you have to position whenever you get a printout of a Smith chart. The more cluster format should come in the right side RHS part. Okay, so you can see here. Okay, so if this is the diagram, let me take the help of this by just I wanted to show like how the position of the Smith chart can be kept. The right hand side should be more number of clusters. You can see here. You can see in this diagram also. See, number of clusters are more in the following. So the number of clusters are more in. So we have to start our Smith chart from this side. Okay. So next, unit circle. You can see this is our unit circle, which you have important labeling parts of the. This is the entire unit circle. You can trace out, and this is our unit resistance circle. That is our unit resistance complete circle. Center and real axis. You also know this. This is our real axis, and the point where the center goes. Center, and this is our real axis. Our real axis. Unit resistance circle, and furthermore, if I go these circles curves are called constant reactance, constant reactance, and the circle you already know, we have drawn it one resistance, constant resistance circle. You know this, not a unit circle but a constant resistance. This entire outer will be the unit circle. So these are few things you can represent on. Now suppose if you want to plot or mark an impedance point on a complex, suppose I want to mark here, suppose I need to mark here. Okay, let me erase this, we'll get back to that. Suppose I need to mark a point here which is above the real axis, and which you can see it's on the constant resistor play circle also, and constant reactance circle also. It is an orthogonal coordinate system, you can directly say that. So if we get a value of r and x, r we know the formula is, we have discussed, r plus jx We have done this. Or you have written in this form also, u plus jv. Okay, where the real axis is u, and the above axis, which is imaginary, and you can say it is jv, uh, jx. This is real axis r u. So this is all. Now if I want to mark a point, we have marked it here, marked a point here. So we get the value of Rn. To find the intersection, now I have to find the intersection of these two. From here where you are getting a circle and reactance, where they are intersecting point. I want to find the intersecting point. Without applying transformation, the value of R and X can be read. See, without calculation, without any applying transformation, or without applying any analytical part, you can directly say what are the values are present here. This intersection point will give the impedance of the following device or the following circuit, whether it is a parallel RLC circuit, whether it is a parallel RLC circuit, or whether it is a series RLC, it is a open circuit, this is a short circuit, this is a pure inductance circuit, this is a pure capacitance circuit. All these can be told using this Smith chart. Hence, it is a very powerful tool for understanding and with less analytical forms. Now, now we see how to use it. Now we will see how to use it in the various lines, in the various lines of transmission calculation. Okay, that just now we told whether it is a pure open circuit, closed circuit, inductance circuit, capacitance circuit, parallel RLC, series RLC. There are so many combinations. That now we will see how we can use the Smith chart to calculate various transmission calculation. So let us go to the next page, saying that let's identify some special points on the Smith chart. Okay, let me take the help of the uh, notes we have used, and we will see how we can be using this. I might use this in the form of a PPT, but labeling and understanding will be more simpler if it is handwritten, and also uh, easier way of understanding through blackboard. Same procedure I'm using. I might use different advanced tools to create PPT, and if it is completely online I would have done that, but we have to do it in terms of how we are doing in our class, the same procedure we are using here also. Okay, let me try with some other like theoretical aspect in the form of PPT in the later parts, and we go for our microwave measurement units. So we'll be using that in the further, and presently we are using our blackboard technique to do the same. Okay, so this is a where we have to identify our Smith chart, special point on the Smith chart. So suppose take this point, take this point, this point, this point, and this. Mark all these points. Okay, so point here in the case 1 or in the case 2, the point A here, we discussed that if I put the range of R values from range from 0 to infinity, X value ranges from 0 to infinity. So let us take R is equal to 0 now and X is equal to 0, and that point is represented as A. When R value A represent R equal to 0, X is equal to 0, resistance and impedance 0, then the circuit which we have drawing a making a point we are plotting on the coordinate will represent a short circuit. We can analyze directly. If there are resistance and impedance are equal to 0, then generally the circuit what we have built is a short circuit. Cannot say that it is having certain power or the voltage which is flowing inside the circuit, right? So in the same way, take one more point, point B here, where the value is R equal to infinity and X equal to infinity. B represents R equal to infinity and X is equal to means it's an open circuit. When we have the highest resistance and the reactant power which is generated, resistance of the reactance which is generated is infinite, then it is called as an open circuit. So the entire power or the entire voltage which is flowing through any point on the circumference of the circle is purely reactance. Any point on the circumference of the circle, unit circle. Suppose here there is a point, here there is a point, here there is a point. All these will represent that it is a purely reactance point. Next, upper of the circle corresponds to positive value of X. Positive value of X means inductive reactance. See, the Smith chart has clearly given few representation here. See, the positive half cycle which is present here will give positive X values. Positive X value represents it is a purely inductive reactance. So here you can say there are inductive reactants which are present in this region from here to here. You can see there are some inductive reactants. Next, the lower half of the circle corresponds to capacitance, which has these values from lower half of the circle is here represents the capacitance of the devices which we are using. So these are few special points. So D represents what you already know, C represents what you already know, A represents what you already know, B represents what you already know. That is about the inductive, this is about the capacitance. Okay, so next we'll go on to the next page number 12. Okay. Now we can see that see, suppose there is a point R. I want to mark a point. Just now in the Smith chart also we did see that we just I just marked a point here. Suppose I want to mark a point here. I will represent this as R. This is my point, capital R. Now I what is this point represent? What does it mean? So let us go back to the R point. Once the point is marked on the Smith chart, immediately you can say whether it is an inductive load or a capacitive load, right? Because the upper half cycle represents it is an inductive, the lower says it is capacitive, right? Upper says the inductive, the lower says the capacitive. So you can say that R is a inductive load we are using. Now we'll see what is C representing. You know that the upper of cycle will represent x is equal to positive value. Suppose x is equal to 1 plus 1. It's a pure reactance. We say that any point on the circumference of the circle represents a purely reactance point, right? Those and the magnitude of this C point, the magnitude of the C point, this point we are saying about, we are talking about, where x is equal to 1 and r is equal to 0 because it is on the axis. R is equal to 0 and x is equal to 1 plus 1 positive value, then the magnitude is equal to the characteristic impedance of the line Z0. Okay, so we have a formula in the previous lectures also. What was the normalization impedance is equal to output impedance by the characteristic impedance. So the magnitude of this point where r is equal to 0 and x is equal to positive 1, then we can straight away say that the magnitude of this point C is equal to the characteristic impedance of the line. Next, D point. D represents r is equal to 0 and x is equal to minus 1. The mirror image of this, no? C's mirror image is D. So r is equal to 0 and x is equal to minus 1. Pure capacitive reactance whose magnitude is equal to the characteristic impedance of the line. It's very important. Pure capacitive value because we know that the lower half circle of the Smith chart represents the capacitance value. The upper part will represent the inductive value. Now we can see that it is the pure capacitance reactance and the magnitude is equal to the characteristic impedance of the line. Normalized impedance is equal to output impedance by the characteristic impedance. We know the main solution. And next, one more major point of the Smith chart is the origin M. M's value r equal to 1 and x is equal to 0, then you can mark that point, right? So uh, impedance at this point, impedance is equal to the characteristic impedance. This is a very important aspect where we can see that matched load. In the lab also we have seen that if I match the load with the output using a magic T, H plane T, E plane, E arm, H arm, magic T. We conducted one experiment on magic T where we were trying to match the load with the other. There was a termination also saying that match termination. What does it do? It actually makes the impedance which is exactly equal to the characteristic impedance, so that there will be hmm? So that there will be, you answer me in the Zoom class, so that there will be, if I do that, what happens, the point on the Smith chart will be at the origin. Means how do you relate this with your magic T, E arm and H arm experiment? You just let me know in the class. Okay. Next. Next we'll go on to page number 13. When number 13 says, let me organize it in the next class, since there was a issue for making this group wise, so that, okay, page number 13. Okay, so let us start this now. Just now we marked a point M, which is at the origin, where impedance is equal to the characteristic impedance. This condition is called as matched impedance. Just now I explained. Now one more important aspect is making the reflection coefficient. See, during the studying, what are the uses of the graphical representation? One important aspect was like, what is the reflection coefficient, what is the position of V max and V minimum, all these things were there. So let us come to this. Now we will understand what is it making, what is to be calculated, like what is from reflection coefficient. In order to get reflection coefficient, what is required, and how the Smith chart changes its modification. It can modify itself for a particular connection devices, parallel, serial. Like what is the modification? It can automatically does without doing transformation or analytical part. So how to hold a Smith chart? Just now I mentioned, like wherever the clusters are more in the right side, then we have to put it in the right side. You know that. I have shown you the graphical diagram also. Conversation of impedance into conversion of impedance into reflection coefficient and vice versa are simpler using Smith chart. See, that is the beauty and the power of the Smith chart. That without having much of the transformation analytics, we can directly convert the impedance into reflection coefficient and reflection coefficient into the impedances. Now we have to define admittance. So why no from nowhere we have to discuss this admittance now? Why not impedance? Till now we discussed impedance. Till now we discussed reactance. All these things. Why suddenly there is a impedance now? Okay. So for this, let me answer, because it is an aggregation of RLC. We still now we discussed only the resistant, inductance, resistance, and reactance, but we never considered a parallel RLC circuit, series RLC circuit. Then what is admittance? It is nothing but the aggregation of all the components which are present. So that is represented as Z, right? So till now we took only resistance and reactance, and there are circuit in real time which connects all the possible devices like resistance, index, and capacitance, which are in parallel or serial. That's why the admittance part will take a very important aspect in this form. So after that, we'll say that so it's a worthwhile to see how the Smith chart gets modified in terms of admittance. Then conversion of impedance into admittance, admittance into impedance will take a transformation part that can also be solved using this method. Let's quick look at it. I have admittance instead of impedance. How will the transformation will be on reflection coefficient of the admittance? Now we have to relate between the reflection coefficient of the impedance and the reflection coefficient of the admittance, because since we are transforming from impedance to admittance, right? So the first task is to define the characteristic of the transmission in terms of admittance, right? So till now we defined the characteristic of the impedance in terms of transmission line. Now the characteristic of the transmission line in terms of admittance is required. That is, the transformation can be only possible through the Smith chart. The second task here after this, in order to plot something, is we have to find the arbitrary admittance and then define the normalized impedance and so on, right? The first thing we started was the normalized impedance and its formula and so on till now. Now what we have to do, we will find a arbitrary position of the admittance. From that point we will identify the we will identify the what we'll identify the normalized impedance and so on, the same procedure from there. So this is possible only using a powerful tool like Smith chart. We'll continue our class with how and when the marking and how to solve a problem. Now we have almost completed the Smith chart aspect. Now we will be going to understand like how to solve a problem using this. I'm sharing an assignment of unit 3 also from this class, and you will be solving and submitting it from the Google Classroom, which I have created. You can log into my Google Classroom and submit your assignment. I have given the last date of submission also. Before that, I want to see everyone to be submitting the assignment, and we will further go with the Smith chart, and we'll go to the unit 4 soon. Okay, so thank you everyone, thank you.